124 light-years away, a telescope has detected a gas that changes everything. On Earth, this molecule forms only one way, through life. The odds of this signal being random? 0.3%. That means a 99.7% chance we found something alive on another world. Today, we journey to K2-18b, a planet 8 times heavier than Earth, orbiting a dying red star where an ocean might hide beneath a poisonous sky. If you enjoy this exploration, like and subscribe. Prepare yourselves. We begin. April 17th, 2025. A team of astronomers stared at data streaming from the most powerful telescope ever built. The wavelengths told a story no one expected. Something 124 light-years away had left its fingerprint in starlight. This fingerprint belonged to a molecule called dimethyl sulfide. 3 letters in the scientific world: DMS. On Earth, this chemical appears in only one way. Life makes it. Nothing else can. The team had been studying an exoplanet designated K2-18b for years. Previous observations hinted at interesting chemistry in its atmosphere: methane, carbon dioxide, maybe water. Those molecules could form through geological processes alone. They told scientists about rocks and heat and pressure, nothing more. But DMS rewrites that story completely. Professor Niku Madhusudan from Cambridge University led the research. His team used an instrument aboard the James Webb Space Telescope called MIRI. This device reads mid-infrared light, wavelengths invisible to human eyes. When K2-18b passed between its star and Webb's mirrors, that starlight filtered through the planet's atmosphere. Molecules in that air absorbed specific wavelengths, leaving dark lines in the spectrum like a cosmic barcode. The pattern matched DMS, or its chemical cousin, dimethyl disulfide, known as DMDS. Both molecules belong to the same family. Both share overlapping features in the wavelength range Webb observes. Future observations might separate them, but for now, scientists know at least one is present. Here comes the critical part. On our world, marine phytoplankton produce DMS. These microscopic organisms drift through oceans by the trillions. When they die and decay, they release this sulfur compound into the air. The smell you notice at the beach, that distinctive ocean scent, DMS creates it. Without constant replenishment from living organisms, DMS vanishes from Earth's atmosphere in days. The Cambridge team detected this biosignature at levels thousands of times stronger than concentrations found on Earth. Our planet has less than 1 part per billion of DMS by volume. K2-18b shows more than 10 parts per million. That difference staggers the imagination. The statistical significance reached what scientists call 3 sigma. This means the probability of these results occurring by random chance sits at 0.3%. Flip that number around, and you get 99.7% confidence. Not absolute certainty, but closer than humanity has ever come before. Madhusudan and his colleagues stress caution. They remain careful with their language. This is not a confirmed detection of life. Unknown chemical processes might produce DMS in conditions completely alien to Earth. The team published their findings in the astrophysical journal Letters, inviting the scientific community to scrutinize every detail. The paper describes independent lines of evidence. Earlier observations using different Webb instruments hinted at DMS, but those signals were weak and ambiguous. The new MIRI data operates in a completely different wavelength range, with no overlap from previous measurements, yet both point toward the same conclusion. Mons Holmberg, a researcher at the Space Telescope Science Institute in Baltimore, worked on the analysis. He watched results emerge through extensive robustness tests. Every check confirmed the signal. Every independent analysis reached the same answer. The scientific process demands skepticism. History teaches harsh lessons about premature celebration. In 2020, researchers claimed to find phosphine on Venus, another potential biosignature. Those results collapsed under scrutiny. Other teams could not reproduce the findings. The phosphine signal turned out to be something else entirely. Will DMS on K218b suffer the same fate? Independent teams worldwide are now analyzing the same Webb data. They will run their own models, apply different statistical methods, search for alternative explanations. If they reach different conclusions, the detection falls apart. If they confirm it, the conversation shifts to something far more profound. But the planet itself holds secrets, even stranger than the molecules floating in its sky. Understanding why DMS matters requires understanding what it is. This molecule consists of 2 carbon atoms, 6 hydrogen atoms, and 1 sulfur atom. The structure looks simple on paper. The implications are anything but simple. Chemists write it as C2H6S, or sometimes in a form that shows its structure more clearly, CH3S, CH3. 2 methyl groups bonded to a sulfur atom in the middle. DMDS has a similar structure, but with 2 sulfur atoms linked together. These sulfur compounds exist in the same chemical family. They share properties. Both give off pungent odors. Both break down quickly when exposed to oxygen and ultraviolet light. Both require specific conditions to form. On Earth, the story of DMS begins in the ocean. Phytoplankton produce a precursor molecule called dimethylsulfonopropionate, mercifully shortened to DMSP by scientists who value their time. These organisms use DMSP to regulate osmotic pressure inside their cells and protect against environmental stress. When the phytoplankton die, bacteria break down DMSP. One of the breakdown products is DMS. The molecule then escapes into the atmosphere. Winds carry it over continents. Chemical reactions in the air transform some of it into sulfate particles. These particles seed cloud formation over oceans, affecting weather patterns and climate. The entire system creates a feedback loop between ocean biology and atmospheric physics. No known geological process on Earth produces DMS in measurable quantities. Volcanoes release various sulfur compounds, like sulfur dioxide and hydrogen sulfide, but not DMS. Hot springs and geothermal vents create other sulfur molecules. Rocks undergoing metamorphism generate different sulfur chemistry altogether. None produce dimethyl sulfide. Laboratory experiments have tried to make DMS without biology. Scientists heated rocks with sulfur compounds. They simulated volcanic conditions. They mixed chemicals under high pressure. Some experiments managed to create trace amounts through complex reaction chains, but these required very specific conditions and produced concentrations far below what biology achieves. This makes DMS what astrobiologists call a biosignature gas, a molecule whose presence in significant amounts suggests biological activity. The key phrase there is insignificant amounts. Finding one molecule does not prove anything. Finding billions upon billions raises eyebrows. DMDS follows similar rules. On Earth, bacteria produce it, decomposition releases it. Again, no significant abiotic source exists. The 2 molecules together strengthen the biosignature case because they come from related biological pathways. The detection on K218b shows concentrations wildly different from Earth. Remember those numbers. Less than 1 part per billion here, more than 10 parts per million there. That represents an increase by a factor of more than 10,000. Does that strengthen or weaken the biological explanation? Some scientists argue it strengthens the case. If you have that much DMS, something must be producing it constantly at enormous rates. The only process we know that does this is life. Massive amounts of it. Others argue the opposite. The concentrations are so extreme that maybe we are seeing something completely different. Some unknown chemistry unique to this alien world. A process that does not exist on Earth because Earth lacks the right conditions. K218b certainly has different conditions. Its atmosphere contains mostly hydrogen, Earth's atmosphere is mostly nitrogen and oxygen. That changes everything about how molecules interact. Hydrogen behaves differently than heavier gases. It absorbs and scatters light differently. Chemical reactions proceed along different pathways. Could hydrogen-rich chemistry somehow generate DMS without life? Theoretical models are being built right now to answer that question. Researchers input the known properties of K218b's atmosphere and let computer simulations run through millions of possible chemical reactions. They search for combinations that produce DMS abiotically. So far, those models have not found a convincing pathway. But absence of evidence is not evidence of absence. Just because we have not thought of the right explanation yet does not mean one does not exist. The molecule keeps its secrets for now. What we know for certain is this: dimethyl sulfide floats in the air of another world. The question that follows shakes the foundations of our understanding. Why is it there? Numbers tell stories if you know how to read them. The 3 sigma detection announced by the Cambridge team translates to a 99.7% confidence level. To most people, that sounds like a slam dunk. Case closed. Life found. Scientists think differently. They demand higher standards before claiming discovery. The gold standard in physics and astronomy is 5 sigma. This represents a confidence level so high that the chance of the result being a statistical fluke drops to 0.00006%. Written differently, that is 6 in 10 million. Astronomers used this threshold when announcing the detection of gravitational waves. Particle physicists used it when confirming the Higgs boson. The bar sits astronomically high for a reason. False positives haunt the history of science. Declaring victory too early leads to embarrassment, retracted papers, and damaged reputations. More importantly, it wastes resources as other teams chase phantoms. The 3 sigma level means there is still a 0.3% chance that random noise created this signal. That might sound tiny, but think of it this way. If you observe 300 similar planets, one of them might show this exact pattern purely by accident. No DMS actually present, just a coincidence in how the light happened to scatter. Observational astronomy deals with this problem constantly. Telescopes collect photons from impossibly faint sources. Electronic detectors convert those photons into digital signals. Noise creeps in at every stage. Cosmic rays strike the sensors. Thermal fluctuations create false readings. Data processing algorithms sometimes generate artifacts. The research team knows all this. Their paper includes extensive robustness tests. They analyzed the data multiple ways using different mathematical techniques. They checked for systematic errors. They compared their findings against simulations of what pure noise would look like. The signal survived every test, but 3 sigma is not 5 sigma. More observations are needed. Specifically, the team estimates that 16 to 24 additional hours of telescope time focused on K218b could push the detection past the 5 sigma threshold. That might not sound like much, just 1 full day of observation. However, the James Webb Space Telescope is the most oversubscribed astronomical facility in history. Thousands of astronomers compete for viewing time. Every hour on Webb requires justification through peer-reviewed proposals. Committees evaluate scientific merit, technical feasibility, and urgency. The DMS team will apply for more time. Other teams might apply as well, hoping to confirm or refute the finding independently. Webb's schedule fills up years in advance, so patience becomes mandatory. Until that 5 sigma confirmation arrives, if it arrives, the detection remains in a strange limbo, not proven, not disproven. Strong enough to take seriously, but not strong enough to celebrate. This uncertainty extends beyond just statistics. Even if the signal strengthens to 5 sigma, scientists must still rule out non-biological explanations. A robust statistical detection only tells you the molecule is really there. It does not tell you where it came from. Consider an analogy. Imagine finding footprints in snow outside your house. You can measure those footprints with incredible precision. You can confirm with 99.99% certainty that they are real impressions, not optical illusions or patterns in the snow. But that measurement alone does not tell you what made them. A person? An animal? A robot designed to leave human-shaped tracks? The DMS detection works the same way. Webb's instruments are incredibly precise. The signal is real. The molecule is there. But proving it came from life requires eliminating every other possibility. Astrobiologists call this the biosignature confirmation challenge. You need multiple independent lines of evidence, all pointing the same direction. You need theoretical models showing why abiotic processes fail to explain the observation. You need follow-up measurements detecting other molecules that should accompany the biosignature if life is responsible. The 99.7% confidence level marks a beginning, not an end. K218b defies categories. When astronomers first discovered it in 2015 using the Kepler Space Telescope, they struggled to classify it. Too big to be called Earth-like, too small to be a gas giant like Jupiter or Saturn. It occupies an uncomfortable middle ground. Planetary scientists use the term sub-Neptune for worlds in this size range. They also call them mini-Neptunes. Neither name helps much because we have no examples in our own solar system. Our family of planets includes small, rocky worlds like Earth and Mars, then jumps straight to massive gas giants. Nothing in between. This creates a knowledge gap. We do not know how sub-Neptunes form. We do not know what they are made of. We cannot study one up close. Every assumption comes from telescopic observations and theoretical models. The planet formed around a red dwarf star, designated K2-18. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. They burn cooler and dimmer than our yellow star, living for trillions of years instead of billions. K2-18 has a spectral classification of M2, 5 volts. The M means red dwarf. The number indicates temperature, with higher numbers being cooler. The V means it is a main sequence star, fusing hydrogen in its core like our own star does. This star sits in the constellation Leo, 124 light-years from Earth. That distance sounds enormous in everyday terms. Light travels at 186,000 miles per second. A light-year represents the distance light covers in one full year, roughly 6 trillion miles. Multiply that by 124 and you get the gulf separating us from K2-18b. The planet orbits its star once every 32.94 days. It circles at a distance of 13.3 million miles. For comparison, Earth orbits at 93 million miles from our star. But remember, K2-18 burns much cooler than our star. That closer orbit places the planet in the habitable zone. The habitable zone represents the range of distances where liquid water could potentially exist on a planet's surface. Too close, and water boils away. Too far, and it freezes solid. K2-18b receives roughly the same amount of energy from its star that Earth receives from ours. However, there is a catch. The habitable zone concept was designed for Earth-like planets with Earth-like atmospheres. K2-18b has neither. Its atmosphere contains mostly hydrogen, which changes everything about how it retains and distributes heat. The planet's mass comes in at 8.63 times Earth's mass. Pack all that into a sphere with a radius 2.61 times Earth's radius. Do the math and you get a density of 2.67 grams per cubic centimeter. That density tells a crucial story. Earth's density is 5.51 grams per cubic centimeter, dominated by an iron core and rocky mantle. Neptune's density drops to 1.64 grams per cubic centimeter because it consists mostly of lighter materials like hydrogen, helium, water, methane, and ammonia. K2-18b falls right between them. This intermediate density suggests the planet might have a rocky core surrounded by enormous amounts of water and ice, all wrapped in a thick hydrogen envelope. But that is just one interpretation. The same density could come from different internal structures, maybe a magma ocean instead of water, maybe no clear separation between layers at all, just a gradual transition from solid to liquid to gas as you move outward from the center. The formation pathway remains uncertain. Did K218b start as a rocky planet that captured a thick atmosphere from the disk of gas surrounding its young star? Or did it begin as a gas-rich world that later lost some of its atmosphere, leaving behind this odd configuration? Both scenarios seem possible. Both have problems. The planet should not exist exactly as we observe it, yet here it sits, defying expectations, and carrying molecules that hint at something even more impossible. Imagine standing on K218b. Your weight would crush you. The planet's mass creates surface gravity roughly 1.3 times stronger than Earth's. Every step would feel like carrying 50 extra pounds. But you would never reach the surface to find out. No solid ground exists to stand on, at least not within reach of where the atmosphere begins. The hydrogen envelope extends downward for hundreds of miles, growing denser and hotter with every mile you descend. The dimensions of this world dwarf our own. Take Earth's radius of roughly 4,000 miles, multiply it by 2.61, you get a sphere more than 10,000 miles across. The volume increases by the cube of that ratio. K218b contains 17 times Earth's volume, yet the mass only increases by a factor of 8.63. This tells you the materials inside must be less dense than Earth's iron and rock. Lighter elements dominate. Hydrogen is the lightest. Water is lighter than rock. Ices of methane and ammonia contribute their mass without adding much density. The planet's gravity well is deep, but not as deep as its mass suggests. Escape velocity at the edge of the atmosphere would be roughly twice Earth's. Chemical bonds between atoms face immense pressure deep below. Under those conditions, matter behaves strangely. Hydrogen, compressed by millions of atmospheres of pressure, stops acting like a gas. It enters a state called metallic hydrogen, where electrons break free from their atoms and flow like a liquid conductor. This form of matter does not exist naturally on Earth. Our deepest ocean trenches only reach pressures around 1,000 atmospheres. K218b's interior might experience millions. Water under extreme pressure and temperature loses its familiar properties. Above 374 degrees Celsius and 220 atmospheres of pressure, water reaches its critical point. It becomes supercritical water, neither liquid nor gas. This strange fluid can dissolve materials that normal water cannot touch. It flows through tiny cracks like a gas, but has density closer to liquid. Some models suggest K218b's interior contains an ocean of supercritical water hundreds of miles deep. Below that, intense pressure might squeeze water into exotic ice formations. These ices remain solid despite temperatures hot enough to melt rock because pressure changes how molecules pack together. At the very center, a rocky or metallic core might exist, or the core could be absent entirely, with just a gradual transition from one phase of matter to another as you descend. We cannot know without seismic data, and seismometers on K218b remain firmly in the realm of science fiction. The thick hydrogen atmosphere creates greenhouse heating. Hydrogen is transparent to visible light but absorbs infrared radiation. Heat from the planet's interior and absorbed starlight gets trapped, unable to escape back to space. This greenhouse effect might keep subsurface regions warm enough for liquid water, even though the planet orbits relatively far from its star. Clouds likely fill the upper atmosphere. These would not be water clouds like on Earth. At the temperatures and pressures found high in K218b's atmosphere, other materials condense. Ammonia ice might form clouds if ammonia is present. Hydrocarbon hazes similar to those on Titan could exist. The exact cloud composition depends on the chemical makeup, which remains uncertain. Light from the red dwarf star would appear dim and reddish. The star produces most of its energy in infrared wavelengths, invisible to human eyes. Standing on a cloud layer beneath that alien sky, you would see a deep crimson disk hanging in a murky atmosphere. No day-night cycle would bring relief. The planet is not tidally locked to its star like many close-orbiting worlds, but its rotation period is unknown. It might spin rapidly, creating fierce winds as the atmosphere tries to redistribute heat. Or it might rotate slowly, leaving one hemisphere permanently lit and the other in perpetual darkness. The scale of this world makes Earth seem fragile and small. Everything is larger, denser, more extreme. And somewhere in that vast envelope of hydrogen and unknown depths, chemicals are being made that should not exist without life. James Webb Space Telescope changed everything. Launched on Christmas Day, 2021, it traveled to a point 1 million miles from Earth, called Lagrange Point 2. There, it unfurled a tennis court-sized sunshield and a hexagonal mirror 21 feet across, made of 18 gold-coated beryllium segments. The gold coating is critical. Gold reflects infrared light better than any other practical material. Infrared wavelengths range from about 0.7 microns to 1,000 microns. Human eyes see wavelengths from 0.4 to 0.7 microns. Everything longer is invisible to us, but not to Webb. Why build a telescope to see what we cannot? Because the universe speaks in infrared. Distant galaxies shift toward red wavelengths as space expands. Cool objects like planets emit infrared rather than visible light. Dust clouds that block visible light become transparent in infrared. The chemical signatures Webb hunts show up most clearly in specific infrared bands. Designing Webb required solving brutal engineering challenges. Infrared detectors only work at extremely cold temperatures. Heat causes electrons to move randomly, creating noise that drowns out faint signals. The telescope's instruments operate at -226 degrees Celsius, just 47 degrees above absolute zero. The massive sunshield makes this possible. 5 layers of material, each thinner than a human hair, sit separated by vacuum gaps. This structure blocks heat from the distant star and Earth, preventing it from reaching the delicate instruments. The side facing away from starlight stays colder than Pluto's surface. 3 main instruments do the science. NIRCam, the near-infrared camera, takes pictures in wavelengths from 0.6 to 5 microns. NIRSpec, the near-infrared spectrograph, splits light into its component colors across the same range. MIRI, the mid-infrared instrument, works from 5 to 28 microns. MIRI detected the DMS signal on K218b. This instrument pushed the boundaries of what engineers thought possible. It requires active cooling beyond what the sunshield provides. A mechanical cryocooler pumps liquid helium, dropping MIRI's temperature to -266 degrees Celsius, just 7 degrees above absolute zero. The optics inside MIRI are miracles of precision. Mirrors and detectors must align to within billionths of a meter. Temperature changes smaller than 1,000th of a degree can ruin observations. Vibrations from the cryocooler needed dampening to prevent image blur. Getting Webb into space took decades of work and $10 billion. The project almost died multiple times from cost overruns and technical setbacks. Congress threatened cancellation. Engineers faced problems that seemed unsolvable. The telescope was originally scheduled to launch in 2007, but got delayed again and again as teams wrestled with complexity. The deployment sequence after launch made everyone nervous. The telescope had to unfold like cosmic origami. Sunshield layers extended, mirror segments locked into place. Everything had to work perfectly on the first try because repairs are impossible at Lagrange Point 2. But it worked perfectly. Every mechanism deployed, every alignment succeeded. The telescope exceeded its design specifications. Webb can detect a bumblebee's heat signature at the distance of the moon. It can measure temperature differences of 1/100th of a degree across a planet's atmosphere. It can spot galaxies so distant their light has traveled for more than 13 billion years. This power comes from combining huge mirror area with perfect cold sensitivity. The larger the mirror, the more light you collect. The colder the detector, the fainter the signals you can see. Webb maximizes both. Observing K218b required pointing Webb at a specific patch of sky for hours, waiting for the planet to cross in front of its star. During that transit, light from K2-18 passed through the planet's atmosphere. Molecules in that air absorbed specific infrared wavelengths. MIRI recorded those absorption features with stunning precision. The data arrived as digital files containing brightness measurements at thousands of individual wavelengths. Scientists then spent months analyzing those files, comparing them to laboratory measurements of known molecules, building models, and testing hypotheses. Without Webb, we would still be guessing about K218b. Only this telescope has the power to read the chemical story written in another world's air. And that story is getting stranger. Picture light as information traveling across space. Every photon carries a message about where it came from and what it encountered along the way. Astronomers decode these messages through a technique called transmission spectroscopy. The method requires patience and perfect timing. You wait for a planet to pass between its star and your telescope. This event is called a transit. From our perspective on Earth, the planet appears as a tiny dark dot creeping across the stellar disk. Transits only happen when orbital geometry aligns correctly. The planet's orbit must be tilted just right so that it crosses our line of sight to the star. Most exoplanets orbit at angles that never produce transits. We detect them through other methods but cannot study their atmospheres this way. K218b transits its star every 33 days. Each transit lasts about 2 hours. During that window, the planet blocks a small fraction of the star's light. The star dims by less than 1%. For a star 124 light-years away, measuring that tiny dip requires extraordinary precision. But the real magic happens in the details. When light passes through the planet's atmosphere on its way to us, molecules in that air interact with specific wavelengths. Each type of molecule absorbs and scatters light differently. Imagine shining white light through red glass. The glass absorbs blue and green wavelengths, letting only red pass through. Molecules work similarly, but with more complex patterns. Water vapor absorbs strongly at certain infrared wavelengths and hardly at all at others. Methane has its own unique pattern, carbon dioxide another, DMS another. These patterns are called absorption lines or absorption features. When you split light into a spectrum, showing brightness at each wavelength, the absorbed regions appear as dips or notches. The shape and depth of each notch identifies the molecule responsible. The technique sounds simple but demands incredible sensitivity. The planet's atmosphere forms a thin ring around its disk during transit. That ring represents a tiny fraction of the total area blocking starlight. The atmospheric signature becomes a subtle change atop an already small signal. Photons from K2-18 take 124 years to reach us. They began their journey in the early 1900s, passing through space while World War I raged on Earth. Each photon carries the same energy it started with, minus whatever got absorbed by the planet's atmosphere. Webb's mirrors collect these ancient photons and focus them onto detectors. Those detectors count individual photons arriving at different wavelengths. The count rates get high enough to measure statistically. Blue wavelengths might register 87 photons per second during transit. Red wavelengths, 93 photons. Infrared at 6 microns might show 112 photons, but infrared at 7 microns drops to 99 photons because methane absorbed some. The team takes these count rates and builds a spectrum, They do this for observations during the transit and compare it to observations when the planet is not transiting. The difference reveals what the atmosphere absorbed. Complications arise constantly. Stars are not perfect, unchanging light bulbs. They have spots and flares and activity that changes brightness. The telescope itself introduces noise. Cosmic rays strike the detectors. Electronic interference sneaks into the signal. Temperature variations affect calibration. Scientists account for all of this through careful data processing. They observe the star many times without the planet transiting to establish a baseline. They model the star's natural variability. They remove systematic effects introduced by the telescope. What remains is the atmospheric signature. For K218b, that signature showed methane at around 3.4 microns wavelength. Carbon dioxide appeared near 4.3 microns. And between 6 and 8 microns, features matching DMS emerged from the data. Each molecule leaves its fingerprint in light. Webb reads those fingerprints with precision unmatched by any previous instrument. The starlight that began its journey more than a century ago tells us about air on another world, potentially filled with the products of alien biology. The method works. The data is real. Now comes the harder part, figuring out what it means. Every atom and molecule in the universe absorbs light at specific energies. This happens because electrons inside atoms can only exist at certain energy levels. When a photon with exactly the right energy hits an atom, an electron jumps to a higher level. The atom absorbs that photon. Later, the electron falls back down, releasing the energy as another photon, often in a different direction. This process creates absorption lines. If you pass white light through a cloud of hydrogen gas and then split that light into a spectrum, you see dark lines where hydrogen absorbed specific wavelengths. Helium creates different lines. Oxygen creates others. Every element has its own signature. Molecules make the picture more complex. When atoms bond together, they can vibrate. The bonds stretch and compress like springs. They can also rotate, spinning in space like tiny tops. Both vibration and rotation require specific amounts of energy. Light can excite these motions. A photon with energy matching a particular vibrational mode gets absorbed. The molecule starts vibrating faster. Another photon might make the molecule rotate. These absorptions happen at wavelengths, determined by the molecule's structure and the strength of its chemical bonds. DMS has a specific structure: 2 carbon atoms, 6 hydrogen atoms, 1 sulfur atom arranged in a particular way. The bonds between these atoms vibrate at frequencies that correspond to infrared wavelengths. When infrared light passes through DMS gas, certain wavelengths get absorbed strongly, others pass through barely affected. Laboratory scientists have measured DMS absorption in great detail. They fill chambers with pure DMS at known temperatures and pressures. They shine infrared light through and record which wavelengths get absorbed. This creates a reference library. When astronomers see matching patterns in exoplanet spectra, they can identify the molecule. But complications arise. Different molecules can have overlapping features. Methane absorbs in some of the same wavelength ranges as DMS. Picking them apart requires high-quality data covering many wavelengths and sophisticated statistical analysis. The MIRI instrument aboard Webb observes from 5 to 28 microns. Within that range, DMS shows several characteristic absorption features. Around 9 microns, a strong feature appears. Other weaker ones exist at different wavelengths. The pattern is distinctive but not unique. DMDS, the related molecule with 2 sulfur atoms, has a similar but slightly different pattern. Its absorption features overlap with DMS in the wavelength range MIRI observed. The team could not definitively separate the two. Either one or both might be present. Temperature affects absorption patterns. Hot molecules vibrate and rotate faster, changing how they absorb light. K218b's atmospheric temperature varies with altitude. upper layers might be cooler than deeper regions. Models must account for this temperature structure. Pressure also matters. At high pressures, molecules collide frequently. These collisions broaden absorption lines, smearing them across wider wavelength ranges. The team had to model the pressure profile of K2-18b's atmosphere to interpret the spectrum correctly. Cloud cover introduces another variable. If thick clouds sit below the atmospheric layer being probed, they reflect light back before it can penetrate deeper. This changes which parts of the atmosphere contribute to the spectrum. The altitude range being sampled shifts. Despite all these complications, the signal persisted. Multiple independent analysis methods reached the same conclusion. Something in K2-18b's atmosphere absorbs infrared light in the pattern characteristic of DMS or DMDS or both. The team compared their observations to computer models. They simulated atmospheres with different compositions and temperatures. They calculated what spectrum each model would produce. The models, including DMS or DMDS, matched the observations far better than models without these molecules. Statistical tests quantified the significance. The presence of sulfur-based molecules explained the data better than any alternative considered. The improvement was strong enough to reach 3 sigma confidence. Light traveled 124 years to deliver this message. The message says, molecules exist around that distant world that should not be there unless something is making them continuously. The question shifts from whether they exist to how they got there. Chemical fingerprints do not lie, but they require careful interpretation to reveal their full truth. The habitable zone concept started simple. Find the range of distances from a star where water can exist as liquid on a planet's surface. Too close and heat vaporizes oceans. Too far and they freeze. Somewhere in the middle lies the sweet spot. This calculation depends on how much energy the star emits and how much the planet reflects. More reflective planets stay cooler because they bounce light back to space instead of absorbing it. Darker planets warm up more. Atmospheric composition changes everything because greenhouse gases trap heat. For a star like ours, the habitable zone extends from about 93 million miles out to about 140 million miles. Earth sits comfortably in the middle. Mars orbits near the outer edge. Venus bakes just inside the inner boundary. K2-18, the red dwarf hosting our planet of interest, outputs much less energy than our star. Red dwarfs burn cooler and dimmer. The habitable zone shrinks closer to the star. For K2-18, that zone sits somewhere between 10 million and 20 million miles out. K2-18b orbits at 13.3 million miles, right in the middle of its star's habitable zone. This placement made the planet interesting even before anyone looked at its atmosphere. A world the right distance from its star to potentially have liquid water, a candidate for deeper study. But the classic habitable zone formula assumes an Earth-like planet with an Earth-like atmosphere. K2-18b breaks that assumption catastrophically. Its thick hydrogen envelope changes how it retains and distributes heat. The greenhouse effect becomes extreme. Hydrogen is transparent to visible light. When red light from the star hits the planet, much of it passes straight through the atmosphere toward whatever surface exists below. That surface warms up and radiates heat back as infrared. But hydrogen absorbs infrared. The heat gets trapped. This creates a runaway effect. More heat trapped means higher temperatures. Higher temperatures mean more infrared radiation trying to escape. More infrared means more absorption by hydrogen. The cycle feeds itself until temperatures soar past what liquid water can tolerate. Some models suggest K2-18b might experience surface temperatures above 374 degrees Celsius. That is the critical point for water. Above this temperature and 220 atmospheres of pressure, liquid water cannot exist. Only supercritical water remains, neither truly liquid nor gas. Other models argue the planet could stay cooler if it reflects enough starlight. High-altitude clouds might act like mirrors, bouncing light back to space before it reaches lower layers. This would reduce the amount of heat entering the system. The challenge is that those clouds must be extraordinarily reflective. Calculations show the planet would need an albedo, a measure of reflectivity, above 0.9. That means reflecting more than 90% of incoming light. Earth's albedo sits around 0.3. Fresh snow reflects about 0.9. The entire planet would need to be more reflective than fresh snow. No one knows if such clouds could form or remain stable. The atmospheric chemistry on K218b differs drastically from Earth. Different molecules condense at different temperatures and pressures. Ammonia might form ice clouds. Hydrocarbon hazes could exist, but whether they achieve the necessary reflectivity remains uncertain. Recent work published just days after the DMS detection challenges the liquid water scenario entirely. A team using updated atmospheric models found that even with perfect cloud reflectivity, the maximum albedo K218b could achieve would be only around 0.17, far too low to prevent runaway heating. This throws the habitability into question. If the surface is too hot for liquid water, where does DMS come from? Could life exist in cooler, upper atmospheric layers? Could organisms float in clouds like some scientists theorize for Venus? The Goldilocks zone is not a simple ring around a star after all. It depends on planetary mass, atmospheric composition, cloud properties, internal heat, and factors we probably have not thought of yet. K218b orbits in the zone, defined by distance and stellar output, but whether it actually has conditions suitable for life remains deeply uncertain. The zone is being reimagined in real time as new data forces new models. Hycean planets emerged as a theoretical concept in 2021. The term blends hydrogen and ocean. These worlds would have thick hydrogen atmospheres surrounding deep liquid water oceans. They represent a completely new category of potentially habitable planets. Niku Madhusudhan and his team at Cambridge University developed the Hycean concept. They realized that sub-Neptune planets, once dismissed as uninhabitable, might offer surprisingly good conditions for life if their internal structure allowed for liquid water beneath hydrogen envelopes. The key insight came from energy calculations. Hydrogen atmospheres trap heat efficiently. This greenhouse effect usually makes planets too hot. But what if the planet formed far from its star, where temperatures start out cold? What if it migrated inward later, ending up in a location where the greenhouse effect warms it just enough to keep water liquid without boiling it away? The models showed this could work. A planet with a rocky core, a deep water ocean hundreds of miles thick, and a hydrogen atmosphere pressing down with thousands of times. Earth's atmospheric pressure might maintain liquid water. The pressure and greenhouse warming would balance out at habitable temperatures. These worlds would be strange beyond imagination. The ocean would not resemble Earth's oceans at all. Pressure increases rapidly with depth. A few miles down, you reach pressures that crush submarines like tin cans. Deeper still, water enters exotic states that do not exist anywhere on Earth. Life in such oceans would face challenges unknown to terrestrial biology. The immense pressure, the lack of solid ground, the hydrogen atmosphere above, hostile to any oxygen-breathing organisms. But life adapts. On Earth, organisms thrive in boiling acidic springs, in frozen Antarctic lakes, in pitch-black ocean trenches. Maybe life could adapt to Hycean conditions too. The atmospheric chemistry would differ from Earth. Hydrogen dominates. Water vapor might be scarce in the upper atmosphere despite vast oceans below, because the hydrogen envelope creates a cold trap. Heat from the star warms lower layers, but upper layers stay frigid, causing water vapor to condense and rain back down. This means telescopes looking at the upper atmosphere might not detect water vapor even if oceans exist. They would see mostly hydrogen with traces of other gases mixed in. detecting biosignatures becomes the key to finding life. Madhusudan's team proposed that methane could be a biosignature on Hycean worlds. Microbes in the ocean might produce methane that bubbles up through the water and escapes into the atmosphere. The hydrogen-rich environment would prevent methane from reacting away quickly. It could accumulate to detectable levels. DMS works even better as a biosignature. It has no significant abiotic source on Earth. If you detect it in significant amounts, biology becomes the leading explanation. DMDS reinforces this because it comes from related biological pathways. K218b became the poster child for Hycean worlds. Its size, mass, and location all fit the theory. Early observations showing methane and carbon dioxide seem to support the hypothesis. The absence of ammonia helped too, because ammonia would dissolve in liquid water oceans, removing it from the observable atmosphere. But not everyone agrees. Other scientists argue K218b might not be a Hycean world at all. It could be a mini Neptune with no liquid ocean, just a thick atmosphere of hydrogen, helium, and other volatiles surrounding a rocky core. The methane and carbon dioxide might form through atmospheric chemistry without needing oceans or life. Or it could be something even stranger, a magma ocean planet with molten rock beneath the hydrogen atmosphere, hot enough to explain the observed chemistry without invoking biology. The hydrogen prevents the magma from cooling, maintaining hellish conditions incompatible with any life we can imagine. The Hycean hypothesis remains just that, a hypothesis. Confirming it would require detecting multiple biosignatures, measuring atmospheric composition in detail, and ruling out alternative explanations. The DMS detection pushes things in that direction but does not close the case. Dozens of other sub-Neptune planets orbit in habitable zones around red dwarf stars. Webb can observe them too. If several show similar biosignature patterns, the Hycean theory strengthens. If K218b stands alone, it might be an anomaly or a misinterpretation. The ocean planet theory offers a tantalizing vision of worlds vastly different from Earth but still capable of hosting life. Whether that vision reflects reality or wishful thinking depends on observations yet to be made. Imagine descending through K218b's atmosphere. The journey would reveal layers of increasing strangeness. You start high above, where the air thins toward space. Here, temperatures hover around -100 degrees Celsius. Hydrogen molecules drift freely, occasionally struck by ultraviolet photons from the distant star. Drifting downward, the atmosphere thickens. Pressure climbs. More molecules pack into each cubic foot of space. The temperature rises slowly at first. At this altitude, clouds might form if the right materials condense. Ammonia ice, perhaps, or hydrocarbon hazes, similar to those shrouding Saturn's moon Titan. The star's light penetrates this region, but appears dim and reddish. K2-18 produces most of its energy in infrared wavelengths. The visible light reaching the planet skews heavily toward red. Any organism with eyes would evolve to see in this crimson twilight. Continue descending. Pressure increases faster now. At 10 times Earth's atmospheric pressure, the air becomes thick enough to feel viscous. Temperature approaches 0 degrees Celsius. Ice particles suspended in the hydrogen might create weather patterns completely alien to Earth. 50 miles down, pressure reaches 100 times Earth's surface pressure. The temperature climbs past 100 degrees Celsius. Water cannot boil because the pressure keeps it liquid even at these temperatures. This region might mark the transition between atmosphere and ocean if the Hycean model is correct. The hydrogen does not disappear. It remains the dominant gas, but now it mixes with water molecules evaporating from the ocean below. The boundary between air and sea becomes blurry. No sharp interface exists like on Earth. Instead, a gradual transition from mostly hydrogen to mostly water spans miles of depth. Below this transition, the ocean begins in earnest, water under immense pressure and moderate heat. The conditions resemble deep hydrothermal vents on Earth, where pressures reach hundreds of atmospheres and temperatures exceed boiling. Life thrives at Earth's vents. Could it exist here? The ocean would be dark. Starlight cannot penetrate through miles of dense hydrogen atmosphere. Any life would have to function without photosynthesis or rely on chemosynthesis, extracting energy from chemical reactions instead of light. Descending deeper into the ocean, pressure continues building. Thousands of atmospheres, tens of thousands. The water's properties change. At 374 degrees Celsius and 220 atmospheres, water reaches its critical point. Beyond this, it becomes supercritical fluid. Supercritical water behaves strangely. It dissolves salts and minerals that normal water cannot touch. It flows through tiny pores with ease. It can act as both solvent and reactant in chemical processes. This fluid might fill much of K2-18b's interior ocean. Even deeper, pressure climbs high enough to squeeze water molecules into exotic ice formations. These high-pressure ices remain solid despite temperatures that would melt normal ice instantly. Different crystalline structures form at different pressures: Ice 7, Ice 10, Ice 11, each with unique properties. The deepest layers might contain ice approaching the planet's core. If a rocky or metallic core exists, it sits buried beneath thousands of miles of water in various states. No drilling rig could reach it. The pressure at that depth exceeds anything achievable in laboratories on Earth. Heat flows from the core outward. Radioactive decay of elements like uranium and thorium generates warmth. Tidal forces from the star might contribute additional heating if the orbit is slightly elliptical. This heat drives convection in the ocean. Hot water rises, cool water sinks. Giant circulation patterns transport heat toward the surface. These currents might bring chemicals from deep layers up to regions where life could potentially exist. Nutrients cycling through the ocean, energy gradients to exploit, the ingredients for biology, if life found a way to start. The hydrogen atmosphere above acts like a lid on a pressure cooker. It prevents the ocean from boiling away into space. It traps heat through the greenhouse effect. It creates the conditions that might allow liquid water to exist at all. But the same hydrogen creates challenges. It provides no oxygen for respiration. Organisms would need to find other chemical pathways to extract energy. Hydrogen sulfide metabolism, perhaps. Methanogenesis. Chemical cycles completely different from Earth's oxygen-based biosphere. If life exists in this alien ocean beneath a hydrogen sky, it would be life stranger than anything in our oceans. Adapted to crushing pressure, thriving in perpetual darkness, producing chemicals that bubble up through the water and drift into the atmosphere where telescopes 124 light-years away can detect them. The picture of a Haitian world remains theoretical, but it rests on solid physics and chemistry. Such planets could exist. The question is whether K2-18b is one of them. Walk along an ocean shore on Earth. Breathe in that distinctive scent. The smell comes from dimethyl sulfide. Phytoplankton produce it by the billions of tons every year. When waves break and spray mist into the air, DMS molecules come along for the ride. These phytoplankton are microscopic organisms drifting in sunlit surface waters. They include species like diatoms, dinoflagellates, and coccolithophores. Despite their tiny size, they make up more biomass than all land plants combined. They produce more than half of Earth's oxygen through photosynthesis. The organisms synthesize a molecule called DMSP for multiple reasons. It helps regulate the salt concentration inside their cells. It provides protection against oxidative stress. It might act as a cryoprotectant, preventing damage when temperatures drop. Evolution has made DMSP essential to their survival. When phytoplankton die or get eaten by zooplankton, bacteria break down DMSP. One breakdown pathway produces DMS. The sulfur-containing gas escapes into the water and then bubbles into the atmosphere. Once airborne, DMS undergoes chemical reactions with oxygen and hydroxyl radicals, forming sulfate particles. These sulfate particles seed cloud formation. Water vapor condenses on them, creating cloud droplets. The process connects ocean biology to atmospheric physics. More phytoplankton means more DMS. More DMS means more sulfate. More sulfate means more clouds. More clouds affect how much sunlight reaches the ocean, feeding back to phytoplankton growth. This cycle has shaped Earth's climate for hundreds of millions of years. It represents one of the most important biogeochemical processes on the planet, and it creates that beach smell everyone recognizes. Annual DMS emissions from Earth's oceans total about 28 million tons. That sounds like a lot, but it represents a tiny fraction of the atmosphere. Concentrations typically stay below 1 part per billion by volume. The gas breaks down quickly. Ultraviolet light from our star destroys it. Oxygen attacks it. Without constant replenishment from phytoplankton, atmospheric DMS would vanish in days. This rapid destruction makes DMS a reliable biosignature. If you detect it in significant amounts, something must be producing it continuously. On Earth, that something is life, always life. Geological processes do not make DMS. Volcanic gases do not contain it. Abiotic chemistry creates only trace amounts under very specific laboratory conditions. The connection between marine life and DMS is so strong that scientists have used it for decades to study ocean health. Satellites measure DMS emissions from space. Ships collect air samples over open water. The data reveals where phytoplankton blooms are happening and how productive different ocean regions are. Now consider K218b. The detected DMS concentrations exceed Earth's by factors of thousands. If the Hessian model is correct, and oceans exist beneath that hydrogen atmosphere, something in those oceans might be producing DMS at rates that dwarf Earth's output. The organisms would not be phytoplankton as we know them. Photosynthesis requires sunlight. K218b's oceans sit beneath miles of opaque hydrogen atmosphere. No photons reach down there. Any life would have to be chemosynthetic, extracting energy from chemical reactions instead of light. Earth has chemosynthetic organisms. They thrive at hydrothermal vents in the deep ocean where no light penetrates. Bacteria and archaea use sulfur compounds, methane, or hydrogen as energy sources. They form the base of entire ecosystems, independent of photosynthesis. Tube worms, clams, and shrimp depend on these microbes. Could similar organisms exist on K218b and produce DMS? The biochemistry would have to differ from Earth. The hydrogen-rich environment, the different temperature and pressure regimes, the absence of oxygen, all these factors would require adaptations unknown in terrestrial life. But biology is creative. Evolution finds ways. If liquid water exists and chemical energy flows, life might emerge. Once started, it might develop metabolic pathways that produce sulfur compounds as byproducts. DMS could accumulate in the ocean and eventually escape into the atmosphere. The smell of the beach on K218b would be overwhelming if you could survive there. Concentrations thousands of times higher than Earth, every breath saturated with sulfur compounds. The scent of an alien biology announcing its existence to the cosmos. Or perhaps not biology at all. Perhaps some unknown chemistry unique to hydrogen-dominated worlds with crushing pressures and moderate temperatures. A process no one has thought of yet. A false positive that mimics life without actually being life. The smell of the beach raises profound questions. It beckons us to answer them. The numbers tell an uncomfortable story. Earth's atmosphere contains DMS at concentrations typically below 1 part per billion by volume. K218b shows concentrations estimated at more than 10 parts per million. That represents an increase by a factor of at least 10,000. Such extreme concentrations challenge both biological and abiotic explanations. If life produces the DMS, that life must be incredibly abundant and productive. If chemistry produces it, that chemistry operates at rates unseen anywhere in the solar system. Consider what 10 parts per million means. In every million molecules of gas floating through K218b's upper atmosphere, more than 10 are DMS. That represents about 0.001% of the total atmosphere by volume. A tiny fraction in percentage terms, but enormous compared to Earth. To sustain those levels, production must exceed destruction. DMS does not last forever in any atmosphere. Chemical reactions break it down. Ultraviolet light from the star photodissociates it, splitting the molecule into fragments. Oxidizers like oxygen or ozone would attack it if present. Without oxygen, DMS might survive longer on K2-18b than on Earth. Hydrogen atmospheres lack the reactive oxygen species that destroy sulfur compounds on our world. But UV light from the star still penetrates the upper atmosphere. Radiation would still break down DMS over time. The team modeled the atmospheric chemistry, trying to understand what production rates would be needed. Their calculations suggest the source must be powerful and continuous. Something generating DMS faster than photochemistry can destroy it. On Earth, all the phytoplankton in all the oceans working constantly produce about 28 million tons of DMS per year. Scale that up to match K2-18b's atmospheric concentrations and you need production rates millions of times higher. Could any biosphere be that productive? Earth's oceans cover 70% of the surface. They receive abundant sunlight driving photosynthesis. K2-18b's hypothetical oceans would cover the entire planet but receive no sunlight in the depths. Chemosynthetic life cannot match photosynthesis's productivity. There is not enough chemical energy available. This discrepancy troubles some scientists. The concentrations seem too high for biology to explain reasonably. Unless K2-18b's life evolved fundamentally different metabolic pathways that produce DMS as a primary product instead of a byproduct. Unless the entire ocean teems with organisms optimized for DMS production, unless conditions exist there that make such production far more efficient than on Earth. All of these possibilities require speculation stacked on speculation, not impossible, but not compelling without additional evidence. The alternative is abiotic chemistry. Could some geological or photochemical process generate DMS at the required rates? Laboratory experiments have produced trace amounts of DMS through reactions involving sulfur compounds and organic carbon under specific conditions. But scaling those laboratory results up to planetary atmospheres requires enormous extrapolation. Some researchers are exploring whether reactions in the planet's interior could produce DMS. If the planet has a hot interior with volcanic activity, gases might rise from below. Those gases could include sulfur compounds and simple hydrocarbons. Reactions at high temperatures and pressures might synthesize DMS. The problem is that such reactions typically produce other sulfur compounds too: hydrogen sulfide, sulfur dioxide, carbonyl sulfide. If abiotic processes made DMS, you would expect to see these related molecules as well. The observations have not detected them so far. DMDS appears alongside DMS in the spectrum. That strengthens the biosignature case, because on Earth, biology produces both through related pathways. But it also complicates the abiotic explanation because now any proposed chemical process must produce both molecules in similar amounts without producing other sulfur species. The extreme concentrations force scientists to consider possibilities outside their comfort zones. Either life exists there in quantities and forms unlike anything on Earth, or chemistry operates in ways we do not yet understand. Neither option fits neatly into existing frameworks. The data insists on an answer. Something is producing these molecules in staggering amounts. Something powerful enough to overwhelm atmospheric destruction processes and maintain concentrations 10,000 times higher than anything in Earth's air. That something awaits identification. The numbers demand an explanation even if none feels satisfactory yet. Dimethyl disulfide shares family ties with DMS. The chemical formula is CH3, SSCH3. Where DMS has one sulfur atom bridging two methyl groups, DMDS has two sulfur atoms linked together. The structures resemble each other. The sources do too. On Earth, Bacteria produce DMDS when breaking down organic matter containing sulfur. Decomposition releases it. The smell of rotting vegetables often includes DMDS alongside other sulfur compounds. It appears in smaller quantities than DMS, but from the same general biological pathways. Some organisms produce DMDS deliberately. Certain bacteria synthesize it as an antimicrobial agent. The molecule interferes with the metabolism of competing microbes, giving DMDS-producing bacteria an advantage. Evolution weaponized this sulfur compound in the microscopic warfare that unfolds in soils and sediments. The molecule's absorption spectrum in infrared light overlaps with DMS. Both show features in the same wavelength regions that Miri observed. This overlap creates ambiguity. The team cannot separate the two with absolute certainty using the current data. Either one or both might be present. This ambiguity actually strengthens the biosignature argument in a subtle way. If an unknown abiotic process were producing the observed spectral features, it would be remarkable if that process mimicked the exact combination of DMS and DMDS that biology produces. Coincidences like that raise eyebrows. Biological systems produce both molecules through related metabolic pathways involving sulfur-containing amino acids. The pathways share enzymes and intermediate compounds. Produce one, and you often get the other as a byproduct or through slight variations in the reaction conditions. DMDS serves additional roles in Earth's ecosystems beyond decomposition. Some plants release it as a defense against herbivores. When insects damage plant tissues, DMDS emissions increase, attracting predators of those insects. The molecule acts as a distress signal, recruiting help from up the food chain. Bacteria in aquatic sediments produce both DMS and DMDS. The ratio between them varies based on temperature, oxygen levels, and the types of microbes present. Warmer conditions favor DMS. Cooler conditions shift the balance toward DMDS. The exact mechanisms are not fully understood even for Earth. On K218b, if both molecules exist, their ratio might reveal something about conditions in the source region. Are they being produced in warm, shallow waters or cold, deep layers? Is the atmospheric chemistry favoring one over the other through selective destruction? These questions matter for interpreting the detection. Future observations with longer exposure times might separate the spectral features. DMDS has absorption lines at slightly different wavelengths than DMS. With better signal-to-noise ratio, those differences become distinguishable. The team plans to request more telescope time, specifically to resolve this ambiguity. Finding both molecules together resembles finding two pieces of a puzzle that fit together perfectly. On Earth, they come as a matched set from biological sources. Finding them together on K218b suggests the same might be true there, unless some extraordinary abiotic process happens to produce both. The sister molecule reinforces the case without proving it. One sulfur compound on an alien world might be a fluke. Two sulfur compounds from the same biological family starts looking like a pattern. Patterns demand explanation. Chemistry on K218b might differ enough from Earth that our assumptions fail completely. Hydrogen atmospheres, extreme pressures, unknown temperature profiles. These conditions could enable reactions that do not occur in terrestrial environments. Maybe sulfur chemistry works differently there. Maybe both molecules form easily through non-biological pathways we have not considered. Or maybe life there produces sulfur compounds in the same basic way life does here because chemistry follows universal rules. Sulfur bonds with carbon in predictable ways. Microbes exploit those pathways for energy and protection. Evolution arrives at similar solutions when faced with similar challenges. The sister molecule stands beside DMS in the spectrum, asking to be explained. Together they form a stronger signal than either alone. Together they point toward an answer that grows harder to dismiss as mere coincidence. K2-18 is not like our star. It belongs to the category called red dwarfs, the most abundant stars in the galaxy. About 70% of all stars fall into this class. They burn cooler, dimmer, and far longer than yellow stars like ours. The star's spectral type is M2, 5 volts. The M indicates red dwarf. The number 2.5 specifies its temperature within that category, with higher numbers being cooler. The V confirms it sits on the main sequence, fusing hydrogen into helium in its core like stars do during their primary lifespan. Surface temperature hovers around 3,400 degrees Celsius. Our star burns at 5,500 degrees. That temperature difference changes the color of emitted light. K2-18 produces most of its energy in infrared wavelengths. Its visible light skews heavily toward red and orange. Blue light barely exists in its output. Any planet orbiting this star receives a very different spectrum of radiation than Earth does. Photosynthesis on Earth evolved to use blue and red light, absorbing those wavelengths with chlorophyll while reflecting green. Photosynthesis on K2-18b, if it exists at all, would have to adapt to infrared heavy illumination. Red dwarfs live for trillions of years. Our star will exhaust its hydrogen fuel in about 5 billion years and swell into a red giant. K2-18 will still be on the main sequence when that happens. Its low mass means it burns fuel incredibly slowly. Stars of this type can remain stable for longer than the current age of the universe. This longevity offers a benefit for life. Stable conditions over immense timescales give evolution more time to work. Complex life on Earth took billions of years to emerge. A planet around a red dwarf could have tens of billions of years or more. But red dwarfs come with hazards. They tend to be active when young, producing frequent flares and eruptions. These flares blast out UV radiation and charged particles. Any planet sitting close to such a star gets bombarded. Atmospheres can be stripped away. Surface water can be split into hydrogen and oxygen that then escape to space. K2-18b orbits at 13.3 million miles. That is close. Only about 1/7 of the distance between Earth and our star. This proximity matters because the star's luminosity is much lower. To receive comparable energy, planets must orbit closer. The close orbit means the planet faces intense UV and X-ray bombardment during flare events. K2-18's age is estimated at several billion years, old enough that flaring should have decreased from the violent early phase. But flares still occur. Each one floods the planet with radiation. A thick hydrogen atmosphere might provide some protection. Hydrogen absorbs UV. The outer layers of atmosphere could act as a shield, taking the radiation hit while protecting anything below. But hydrogen can also photodissociate, splitting into individual atoms that escape to space if they achieve escape velocity. Over billions of years, atmospheric erosion becomes significant. Models suggest K2-18b might have lost several Earth masses worth of hydrogen since it formed. The planet started with an even thicker envelope that has been gradually whittled away by stellar radiation. The star's red light creates perpetual twilight on the planet. No bright blue sky, no brilliant sunrise, just dim crimson illumination filtering through a hydrogen haze. Shadows would be soft and diffuse. Visibility might extend for miles through the murky atmosphere, everything tinted in shades of orange and brown. Tidal effects might play a role too. Orbiting so close to its star, the planet feels gravitational pulls that raise tides. If oceans exist, they would bulge toward and away from the star. Internal friction from these tides generates heat. This tidal heating adds to the planet's energy budget, potentially helping maintain liquid water even farther from the star than simple calculations suggest. The orbit takes 33 days to complete. From the planet's surface, the star would appear to move across the sky in a monthly cycle. If the planet rotates, day and night would come and go on a different schedule. If tidally locked, one hemisphere would face the star perpetually, while the other froze in eternal darkness. Current data does not tell us the rotation period, That measurement requires techniques not yet applied to K2-18b. The planet keeps some of its mysteries. A dying red star is a misnomer, actually. K2-18 is not dying, it is in its prime. Red dwarfs do not die in the traditional sense for trillions of years. But the phrase captures the alien nature of this star. Cool, dim, long-lived, active, orange-red in color. Nothing like the bright yellow star that lights Earth. Life, if it exists around K2-18, evolved under very different conditions than life here. The embrace of that red star shapes everything. K2-18b completes one orbit in 32.94 Earth days, less than a standard month. This rapid orbital period places it firmly in the category of hot or warm sub-Neptunes depending on temperature estimates. Compare this to Earth's 365-day orbit, or Mars at 687 days. Even Mercury, the closest planet to our star, takes 88 days. K2-18b races around its star more than twice as fast as Mercury. The speed makes sense given the orbital distance. Kepler's laws dictate that closer orbits have shorter periods. At 13.3 million miles from K2-18, gravitational forces are strong. The planet must move quickly to maintain orbit instead of falling inward. Orbital velocity reaches about 46 miles per second. Earth travels at about 18.5 miles per second. K2-18b moves 2.5 times faster. This speed results from the same physics that governs satellites and space stations. The rapid orbit creates interesting observational opportunities. Transits happen frequently. Every 33 days, the planet crosses in front of its star from our perspective. This regularity allows astronomers to schedule observations efficiently. Wait a month, catch the next transit, gather more data. Multiple transits observed over time also reveal subtle details. The planet's orbit is not a perfect circle. Small variations in timing from one transit to the next indicate orbital eccentricity. K2-18b's eccentricity appears low but non-zero. The orbit is slightly elliptical. This eccentricity matters for habitability. An elliptical orbit means the distance to the star varies over each orbit. The planet experiences changing energy input. At closest approach, it receives more radiation. At the farthest point, less. These variations drive temperature changes. Tidal heating increases with eccentricity. As the planet's distance from the star changes, gravitational forces flex it. Internal friction from this flexing generates heat. Too much eccentricity could cook the planet from within. K2-18b's low eccentricity keeps tidal heating modest. The 33-day year raises questions about seasons. Earth's seasons come from axial tilt, not orbital distance. As Earth orbits, its tilted axis points different hemispheres toward or away from our star. K2-18b's axial tilt is unknown. It could be anywhere from 0 degrees, no tilt, to 90 degrees, extreme tilt. Without knowing the tilt and rotation period, predicting weather and climate patterns becomes speculative. If the planet rotates rapidly, atmospheric winds would redistribute heat efficiently. If it rotates slowly or is tidally locked, temperature extremes would be severe. Tidal locking happens when orbital period equals rotation period. The same hemisphere always faces the star. This occurs commonly for planets orbiting close to their stars. Our moon is tidally locked to Earth. Observations suggest some exoplanets are tidally locked too. K2-18b might be tidally locked. The close orbit and tidal forces favor this outcome over billions of years, but direct confirmation requires measurements not yet available. If locked, the day side would be hotter and the night side colder. Atmospheric circulation would struggle to transport heat across the temperature gradient. A permanent day side under dim red starlight. a permanent nightside plunged into cold darkness, broken only by starlight from the rest of the galaxy. The twilight zone between them might offer the most temperate conditions. Life, if it exists, might concentrate there. Or perhaps the thick hydrogen atmosphere prevents tidal locking. Atmospheric tides can transfer angular momentum, keeping the planet spinning. Jupiter's moon Io experiences something similar. Tidal heating and atmospheric effects balance out, maintaining a rotation that is not locked to its orbit. The 33-day year packs a lot of dynamics into a short time. Changes that take Earth a full year to cycle through happen in a month on K2-18b. If seasons exist, they flash by. If climate oscillates, it does so rapidly. If life exists, it experiences a world where time moves differently. Observing these rapid cycles gives astronomers an advantage. Multiple years of data can be collected in months of real time. Long-term trends reveal themselves quickly. The planet's fast clock becomes an asset for research, even as it creates an alien environment unlike anything in our solar system. Before the DMS detection, methane captured scientific attention. The Cambridge team detected it during earlier observations using different Webb instruments. Methane appeared strongly in the spectrum at wavelengths around 3.4 microns. Methane is CH4, one carbon atom bonded to 4 hydrogen atoms. It forms easily in nature through many processes. Geological activity produces it when rocks react with water at high temperatures. Volcanic gases contain methane. Comets have methane ice. But methane in an atmosphere requires an active source. The molecule does not last long. Ultraviolet light from stars breaks it down through photolysis, splitting it into carbon and hydrogen fragments. Those fragments then react with other atmospheric constituents to form different molecules like ethane, acetylene, and more complex hydrocarbons. Without continuous replenishment, atmospheric methane vanishes relatively quickly. On Earth, methane has an atmospheric lifetime of about 12 years before photochemical destruction removes it. The atmosphere stays at roughly 1.9 parts per million, only because sources constantly add more. Those sources include both geological and biological processes. Natural gas leaks from the ground. Wetlands produce it through bacterial decomposition of organic matter. Termites generate it in their guts. Livestock release it through digestion. Human activities add more through fossil fuel extraction and agriculture. About 60% of Earth's methane comes from biological sources. Methanogenic bacteria in anaerobic environments produce it as a metabolic waste product. These organisms extract energy from chemical reactions that generate methane as a byproduct. K2-18b's methane concentrations dwarf Earth's. The spectrum shows abundances around 1% by volume. That is thousands of times higher than our planet. Such high concentrations demand a powerful source. Could geology explain it? If the planet has active volcanism or hydrothermal systems, gases from the interior might include abundant methane. Carbon and hydrogen are common elements. Under the right pressure and temperature conditions, they combine to form methane. Models of K2-18b's interior chemistry suggest methane could form deep below the surface. If the planet has a rocky core overlaid by a water ocean and then a hydrogen atmosphere, reactions at the interface between ocean and rock might generate methane. That gas could then rise through the water and escape into the atmosphere above. But there is a problem. If this geological methane production were efficient, you would expect other gases to appear alongside it. Hydrogen sulfide from sulfur-bearing minerals, carbon monoxide from incomplete carbon reactions, ammonia from nitrogen compounds. The observations do not show these other gases in expected proportions. The alternative is biology, methanogenic organisms producing methane in vast quantities. On Earth, these organisms thrive in environments lacking oxygen. Ocean sediments, rice paddies, the guts of animals, deep subsurface environments. They use various metabolic pathways but all generate methane. If K218b's hypothetical oceans host methanogenic life, that life could be producing the observed methane, the hydrogen-rich environment would suit such organisms well. They could use hydrogen as an energy source, combining it with carbon dioxide to make methane. This reaction releases energy that the organisms capture. The chemistry works on paper. The question is whether such organisms could evolve and thrive in K218b's conditions. The crushing pressure, the lack of sunlight, the alien elemental abundances. These factors create an environment nothing like Earth's. Some researchers have modeled what methanogenic ecosystems might look like on Hycean worlds. Their calculations show that such ecosystems could maintain methane at the observed levels if enough biomass exists. The numbers require oceans teeming with microbial life, but not impossibly so. Methane alone is not a strong biosignature. Too many abiotic sources exist, but methane combined with other gases becomes more interesting. Methane and oxygen together would be compelling because those gases react with each other. Their coexistence requires constant replenishment from separate sources. K218b has no detected oxygen, but it does have carbon dioxide and now DMS or DMDS. That combination tells a different story. Methane-producing organisms and sulfur-cycling organisms potentially working in the same environment. Multiple metabolic pathways operating simultaneously. The methane that doesn't belong according to simple geology might belong perfectly in a biological framework, or it might come from chemistry too complex for current models to capture. The molecule raises as many questions as it answers. Carbon dioxide appeared in the spectrum alongside methane. The wavelength signature showed up clearly around 4.3 microns. CO2, one carbon atom bonded to two oxygen atoms. A molecule so common in the universe that finding it surprises no one. Earth's atmosphere contains about 420 parts per million of carbon dioxide. Venus has an atmosphere that is 96% CO2. Mars sits at 95%. The molecule forms easily whenever carbon and oxygen exist together. Volcanic outgassing produces it. Combustion releases it. Even simple weathering of rocks generates CO2 over geological timescales. On K218b, concentrations reach several percent by volume, thousands of times higher than Earth. This abundance makes sense for a planet with a thick hydrogen atmosphere. Carbon dioxide is heavy enough to stick around despite the planet's gravity. It does not escape to space easily, like lighter molecules might. The presence of both methane and carbon dioxide creates a chemical puzzle. These two gases react with each other when given the opportunity. Methane is reduced, meaning it wants to give up electrons. Carbon dioxide is oxidized, wanting to accept electrons. Mix them together with energy input, and you get reactions that convert them to other molecules. On Earth, this does not happen much in the atmosphere because the molecules rarely interact directly. They need catalysts or extreme conditions to react. But over geological time, or in the presence of certain minerals or biological activity, the two can react to form water and carbon monoxide or other organic compounds. K218b's atmosphere contains both in abundance. The fact that they coexist suggests either they are being produced faster than they react away, or conditions prevent the reactions from proceeding efficiently. Both scenarios tell us something about the planet. If production outpaces destruction, something must be generating huge amounts of both gases constantly. For carbon dioxide, volcanic outgassing seems plausible. For methane, we have discussed geological and biological possibilities. Having both requires either multiple active processes or one unified process that makes both simultaneously. Some scientists propose that reactions in the planet's interior could produce the gas mixture. Carbon-bearing minerals reacting with water at high temperatures and pressures might yield both methane and carbon dioxide depending on exact conditions. The ratio between them depends on temperature, pressure, and the oxidation state of the environment. The oxidation state matters tremendously. In a reducing environment with lots of hydrogen, chemical reactions favor making methane. In an oxidizing environment with oxygen available, reactions favor carbon dioxide. K218b apparently has both, suggesting conditions that shift between states or regions with different chemistry. Another possibility involves phase transitions in the interior. If the planet has layers at different temperatures and pressures, different chemistry occurs in each layer. Deep, hot regions make carbon dioxide. Shallower, cooler regions make methane. Both gases migrate upward and mix in the atmosphere. Biology offers an alternative explanation. Different organisms using different metabolic pathways, some producing methane through methanogenesis, others producing carbon dioxide through respiration or fermentation. On Earth, diverse microbial communities create complex mixtures of gases. The same could happen on K218b. The carbon dioxide detection also helps constrain the planet's temperature and atmospheric structure. CO2 absorption features are sensitive to temperature. By analyzing the exact shape and depth of the absorption lines, scientists can estimate the temperature at different atmospheric layers. Those temperature estimates feed into models of the planet's climate. They help determine whether liquid water could exist. They constrain how much heat the greenhouse effect traps. They reveal whether the atmosphere is stable or undergoing rapid chemical evolution. The ratio of carbon dioxide to methane also matters. Too much CO2 compared to methane might indicate geological processes dominating. Too much methane compared to CO2 might suggest biological activity. The observed ratio falls somewhere in between, not clearly favoring one explanation over another. What makes the mixture truly interesting is what is missing. If methane and carbon dioxide are reacting to form other compounds, where are those compounds? Carbon monoxide should appear. More complex organics should build up. Some observations hint at these molecules, but the signals are weak and uncertain. The carbon dioxide sits in the spectrum, a piece of the puzzle that fits with some theories and contradicts others. Combined with methane, DMS, and the absence of other expected gases, it paints a picture of atmospheric chemistry unlike anything in the solar system. The mix of gases demands explanation. Every proposed model struggles to account for all observations simultaneously. The chemistry refuses to settle into a neat category. Ammonia should be there. Models of sub-Neptune atmospheres predict it. Chemistry involving nitrogen and hydrogen favors its formation. Yet observations show no ammonia in K218b's upper atmosphere. This absence speaks as loudly as any detection. Ammonia is NH3, one nitrogen atom bonded to 3 hydrogen atoms. In hydrogen-rich environments, nitrogen naturally combines with hydrogen to form this molecule. Jupiter and Saturn have ammonia clouds in their atmospheres. So does Uranus and Neptune. Any world with abundant hydrogen and nitrogen should produce ammonia. The Cambridge team searched for ammonia's spectral signature carefully. They knew it should be there. The instruments were sensitive enough to detect it if present at expected levels. The data came back negative. No ammonia features appeared in the spectrum. This non-detection requires explanation. Either ammonia never formed in significant amounts, or something removed it, or it exists but hides below the atmospheric layers that telescopes probe. One possibility involves solubility. Ammonia dissolves readily in liquid water. If K218b has a global ocean beneath its hydrogen atmosphere, ammonia from the atmosphere would dissolve into that ocean. The water acts like a giant sponge, pulling ammonia out of the air and locking it in solution. On Earth, rain scrubs gases from the atmosphere. Ammonia is particularly water-soluble. When it rains, ammonia dissolves and falls to the surface. The atmosphere maintains low concentrations only because biological processes and industrial sources keep adding more. K218b might experience a similar process. If water vapor rises from an ocean, condenses in the cooler upper atmosphere, and rains back down. That rain would capture any ammonia present. The cycle would transfer ammonia from atmosphere to ocean continuously. This scenario actually supports the Hycean world hypothesis. The absence of ammonia becomes evidence for a liquid water ocean rather than evidence against habitability. A planet without an ocean would retain its ammonia in the atmosphere. A planet with oceans loses it to the water. Another explanation involves chemistry at different altitudes. Perhaps ammonia does exist in lower atmospheric layers where temperatures and pressures are higher. But in the upper atmosphere where Webb observes, photochemical reactions destroy it. Ultraviolet light from the star breaks ammonia apart. The nitrogen and hydrogen separate, forming other compounds. Models of atmospheric photochemistry on hydrogen-rich worlds show that ammonia can be depleted in upper layers, even when abundant lower down. The vertical structure matters. What you see depends on which altitude range the observations sample. Temperature plays a role too. Ammonia condenses into ice at certain temperatures and pressures. If conditions in K218b's atmosphere favor ammonia ice cloud formation, the clouds would remove gaseous ammonia from the observable regions. The molecule would still exist but locked in solid form. Some researchers argue the missing ammonia contradicts the mini-Neptune interpretation. If K218b were simply a gas-rich planet like a small version of Neptune, ammonia should be detectable. The fact that it is missing suggests something different is happening. Either oceans are scrubbing it out, or the planet formed in a way that left it nitrogen poor. Nitrogen abundance in planetary atmospheres depends on formation history. If K218b formed far from its star, where temperatures were very cold, nitrogen might have been incorporated as solid ice in the original building blocks. As the planet grew, that nitrogen became trapped in the interior, never reaching the atmosphere in large amounts. Alternatively, if the planet formed closer to its star and migrated outward later, nitrogen might not have condensed at all during formation. It would have remained in the gaseous disk and been lost. This would leave the planet depleted in nitrogen and therefore lacking ammonia. The missing ammonia also affects biosignature interpretation. On Earth, ammonia is a product of biological nitrogen fixation. Certain bacteria convert atmospheric nitrogen into ammonia, which plants then use. If K218b had similar biology, you might expect ammonia to appear. Its absence suggests either no nitrogen-fixing biology exists, or the oceans dominate the ammonia cycle completely. Any ammonia produced by organisms dissolves in water before accumulating in the atmosphere. This would actually make the ocean biology more like Earth's ocean systems, where ammonia concentrations in seawater dwarf atmospheric amounts. The mystery deepens when you consider that nitrogen is the fifth most abundant element in the universe. It should be present. Where did it go? Why is it not showing up as ammonia or other nitrogen compounds? Some nitrogen might exist as molecular nitrogen, N2, which is extremely difficult to detect through transmission spectroscopy. The molecule lacks a permanent dipole moment, making it nearly invisible to the techniques Webb uses. K218b could have abundant nitrogen gas that simply does not show up in observations. The missing ammonia serves as a constraint. Whatever model you propose for K218b must explain why this expected molecule fails to appear. That constraint narrows the possibilities and forces more sophisticated thinking about the planet's composition and history. Absence of evidence becomes evidence of something. The question is evidence of what exactly? The missing ammonia keeps its secrets while eliminating some scenarios and supporting others. Not everyone accepts the Hycean world interpretation. Some scientists argue K218b might be something far worse than a lifeless ocean planet. It could be a world of molten rock beneath a poisonous sky, a magma ocean planet masquerading as potentially habitable. The alternative model starts with the planet's energy budget. K218b receives radiation from its star. It has internal heat from radioactive decay and possibly tidal forces. All this energy must go somewhere. If the greenhouse effect from the thick hydrogen atmosphere is strong enough, temperatures could soar far past the boiling point of water. Calculations show that planets with hydrogen atmospheres experience extreme greenhouse heating. Hydrogen is transparent to visible light but absorbs infrared. Heat gets trapped efficiently. The surface temperature depends on how much starlight reaches it and how effectively the atmosphere prevents heat from escaping back to space. Some models suggest K218b's surface temperature might exceed 1000 degrees Celsius. At those temperatures, rock melts, silicates become liquid. The surface would be an ocean of glowing magma, slowly churning as convection currents transport heat. Magma oceans are not hypothetical. Earth likely had one shortly after forming, when impacts and gravitational compression generated enormous heat. The entire surface was molten. As the planet cooled over millions of years, a solid crust formed on top. K218b might be stuck in an earlier phase, too hot to solidify. The thick hydrogen atmosphere prevents cooling. It acts like an insulating blanket. Heat from below cannot escape efficiently. The magma ocean persists indefinitely unless something changes the atmospheric composition or mass. This hellish scenario actually explains some observations better than the Hiceian model. Magma reacting with a hydrogen atmosphere could produce methane and carbon dioxide through high-temperature chemistry. Dissolve carbonate minerals in molten rock and CO2 outgases. React carbon-bearing magma with hydrogen and you get methane. The ratios of gases observed might reflect equilibrium chemistry at magma temperatures rather than biological activity. No life needed, just thermodynamics operating at extreme conditions. Ammonia would dissolve in magma just as it dissolves in water. The missing ammonia fits this model too. Any ammonia formed in the atmosphere would be pulled down to the surface, where it reacts with molten silicates. The magma scrubs ammonia out just like an ocean would. But what about DMS? Can magma chemistry explain that biosignature? This becomes the crucial test. On Earth, we have no examples of geological processes producing significant DMS. Volcanoes do not emit it. Hydrothermal systems do not make it. Magma does not contain it. Proponents of the magma ocean model argue that K218b's chemistry might be exotic enough to produce DMS abiotically. Sulfur is common in magmas. Carbon is present. Hydrogen saturates the atmosphere. Under the extreme temperatures and pressures, perhaps reactions occur that do not happen on Earth. Laboratory experiments have tried to test this. Scientists heat sulfur compounds and carbon sources together in hydrogen-rich environments, trying to synthesize DMS without biology. Some experiments produce trace amounts, but scaling those traces up to explain K218b's concentrations requires assumptions about reaction efficiency and transport mechanisms. The magma ocean model faces another challenge. Such a hot surface should emit thermal radiation detectable by Webb. The planet should glow in infrared. Observations have not clearly detected this thermal emission yet, though more data is needed to rule it out conclusively. Temperature estimates from the spectral analysis also create problems for the magma model. The observed absorption features suggest atmospheric temperatures cooler than expected for a planet with a magma ocean beneath. The temperature gradient does not match predictions. Raymond Pierre Humbert, a planetary physicist at Oxford, advocates for the hot interpretation. His calculations show that greenhouse heating on K218b would be intense. He argues that liquid water oceans are implausible, and if water exists at all, it would be in a supercritical state, or as vapor mixed with the hydrogen. Sarah Seeger at MIT urges caution based on historical precedents. Previous claims about K218b turned out to be wrong. Early observations suggested water vapor that later proved to be methane. She warns against overinterpreting sparse data. The magma ocean alternative represents the pessimistic extreme. Instead of a world possibly teeming with life, we have a hellscape utterly hostile to any biology. molten rock, crushing pressures, searing heat, toxic atmosphere, a planet where nothing lives and nothing can. If this model is correct, the DMS detection becomes a cautionary tale about biosignatures, a warning that molecules we associate with life might form through exotic chemistry in environments nothing like Earth. A reminder that the universe is stranger than our limited experience suggests. Hell itself might be producing the signals we desperately want to interpret as life. The data supports both possibilities. More observations will tip the balance one way or the other. For now, heaven and hell remain equally viable explanations. Greenhouse effects keep Earth habitable. Without atmospheric gases trapping heat, our planet's average temperature would plunge below freezing. Water vapor, carbon dioxide, and methane create a warming blanket that maintains temperatures suitable for liquid water and life. But greenhouse effects can run away. They can become self-reinforcing feedback loops that turn temperate planets into hellscapes. Venus demonstrates this catastrophically. Venus likely started with oceans similar to Earth's. Water covered its surface. The planet orbited closer to the young star, receiving more energy, but not impossibly so. Something happened. Temperature increased slightly. More water evaporated. Water vapor is a powerful greenhouse gas. More water vapor meant more warming. More warming meant more evaporation. The cycle accelerated. Eventually, temperatures climbed so high that oceans boiled completely. All that water vapor entered the atmosphere, creating extreme greenhouse heating. Temperatures soared past 450 degrees Celsius, hot enough to melt lead. The water molecules in the upper atmosphere then photodissociated. Ultraviolet light split them into hydrogen and oxygen. Hydrogen escaped to space. Oxygen reacted with surface rocks. Venus lost its water. It ended up with a thick carbon dioxide atmosphere crushing down at 90 times Earth's surface pressure. Surface temperatures reached 870 degrees Fahrenheit. A runaway greenhouse turned a potentially habitable world into an oven. K218b faces similar risks. The thick hydrogen atmosphere creates greenhouse heating far exceeding anything Earth experiences. Hydrogen absorbs infrared radiation efficiently. Heat from the star and from the planet's interior gets trapped. Models calculate the threshold where greenhouse effects run away. For planets with hydrogen atmospheres, that threshold depends on stellar irradiation, atmospheric mass, and albedo. The calculations show K218b sits dangerously close to or beyond the runaway limit. If the planet started with surface water, the greenhouse effect might have boiled it all into the atmosphere over geological time. Water vapor mixing with hydrogen creates intense warming. Temperatures climb, more water evaporates. Positive feedback dominates. Breaking this cycle requires removing heat somehow. Clouds could help if they reflect enough starlight back to space before it warms the planet. But clouds also trap infrared heat themselves. Whether they cool or warm the planet depends on their altitude, thickness, and composition. For K218b to maintain liquid surface water, it would need clouds that reflect more than 90% of incoming starlight, according to some calculations. Such extreme reflectivity seems unlikely. Clouds on Earth achieve albedos around 0.5 to 0.7 at best. Achieving 0.9 requires near-perfect mirrors floating in the atmosphere. The runaway threat also depends on water availability. If the planet formed with limited water, the greenhouse effect cannot run away as easily. You need abundant water vapor to create the strongest positive feedback. A planet with mostly hydrogen and small amounts of water might heat up, but not catastrophically. This introduces another possibility. Maybe K218b is in a transitional state. It had oceans once. The runaway greenhouse is in progress. Surface water is boiling away. In a few 100 million years, the process will complete and the planet will resemble Venus, but with a hydrogen atmosphere instead of carbon dioxide. The detected molecules could be products of this dying ocean. Life that evolved in happier times now struggling as conditions deteriorate. DMS and methane released from dying ecosystems. A final gasp before the oceans vanish and the hydrogen atmosphere blows away any remaining volatile compounds. Or perhaps the planet found an equilibrium that avoids runaway. Maybe the hydrogen atmosphere is massive enough that its pressure prevents water from boiling even at high temperatures. Under extreme pressure, the boiling point increases. At thousands of atmospheres of pressure, water remains liquid at temperatures that would vaporize it at Earth's surface. This creates a strange scenario where the ocean is extremely hot but still liquid, held down by crushing atmospheric weight. Life in such an environment would have to be thermophilic, adapted to temperatures exceeding boiling. Earth has organisms that thrive at 110 degrees Celsius in deep-sea vents. Extrapolate that to higher temperatures and maybe K218b's biology exists in a pressure cooker ocean. The runaway greenhouse threat hangs over every Hycean world hypothesis. Hydrogen atmospheres are double-edged swords. They might create conditions for liquid water where it otherwise could not exist. Or they might create inescapable heat traps that destroy any chance of habitability. Which scenario applies to K218b remains unknown. The planet balances on a knife edge between potentially habitable and definitely hellish. Small changes in parameters tip the conclusion one way or the other. The threat reminds us that habitable zones are not simple rings around stars. They are complex regions defined by multiple factors interacting in non-linear ways. Greenhouse effects make those interactions especially treacherous. Water has a critical point. Push it past 374 degrees Celsius and 220 atmospheres of pressure, and something strange happens. The distinction between liquid and gas vanishes. Water enters a state called supercritical fluid. Supercritical water is neither liquid nor gas, but both simultaneously. It has density approaching liquid water, but flows like gas. It fills containers completely like gas, but dissolves materials like liquid. The properties are bizarre and useful for industrial chemistry on Earth, but terrifying to contemplate on a planetary scale. At the critical point, the meniscus between liquid and gas disappears. If you watch water approach this threshold in a sealed vessel, you see the boundary between liquid and vapor shimmer and fade. Above the critical point, only one phase exists. Call it what you want, the labels stop meaning anything. Supercritical water behaves as an extraordinary solvent. It dissolves salts and minerals that normal water cannot touch. It penetrates materials with ease. Industries use it to extract caffeine from coffee beans, to break down toxic waste, and to process biomass into useful chemicals. On K218b, if the planet is hot enough and the atmosphere presses down hard enough, any water below the surface might exist entirely in supercritical state. No liquid ocean in the traditional sense. No gas phase water vapor, just supercritical fluid extending for hundreds of miles downward. This state changes everything about potential habitability. Life as we know it evolved in liquid water. Cells are bags of aqueous solution surrounded by lipid membranes. Chemical reactions occur in water's unique environment. Proteins fold into specific shapes based on their interactions with water molecules. Could life exist in supercritical water? We have no examples. Earth's organisms live in liquid water. Even extremophiles that tolerate high temperatures and pressures still live in liquid water. The critical point represents an absolute barrier in terrestrial biology. Supercritical water might be too chaotic for life. Molecular interactions change. Hydrogen bonding, so critical to biochemistry, weakens and disappears at supercritical conditions. Organic molecules might not be stable. Anything resembling a cell membrane would likely fail, yet ruling out life completely feels premature. Life adapts to extreme conditions. Earth's biosphere includes organisms living at 110-degree water in deep-sea vents under 300 atmospheres of pressure. Not quite supercritical, but approaching the threshold. Maybe alien biochemistry evolved differently. Maybe supercritical fluids support life forms using molecular machinery, unlike anything on Earth. Carbon bonds with other elements in countless ways. Silicon, nitrogen, sulfur, phosphorus, all create complex molecules. Perhaps some combination works in supercritical environments. The phase diagram for water shows the critical point clearly. Below it, liquid and gas phases separate with a distinct boundary. Above it, only one fluid phase exists. Temperature and pressure define everything. K218b's interior might span this diagram. Upper layers where hydrogen dominates might be cool enough for water vapor or ice. Middle layers might have liquid water if pressure and temperature balance correctly. Deep layers would push into the supercritical regime. Determining which layers exist requires knowing the planet's internal heat flow. Radioactive decay generates heat. Tidal forces might add more. This heat conducts outward. Where temperatures and pressures intersect determines what phase water takes. Recent modeling efforts map these possibilities. Some scenarios show entirely supercritical water below a hydrogen atmosphere with no liquid ocean anywhere. Other scenarios find a thin shell where conditions permit liquid water sandwiched between supercritical fluid below and vapor above. If the DMS detection is real and biological in origin, life would have to exist in whichever layer permits it. A supercritical water ocean rules out life as we know it, but maybe not life as it could be. A liquid water layer somewhere in the middle offers more familiar possibilities. The uncertainty about the planet's interior state makes biosignature interpretation treacherous. You cannot assess habitability without knowing whether liquid water exists. You cannot know what form water takes without detailed atmospheric models and measurements of the planet's heat budget. Supercritical water represents the edge of the unknown, a state of matter common in industrial processes, but alien in planetary contexts. K218b might be the first world where we confront this state on a global scale. The molecules in supercritical water still form hydrogen bonds, but those bonds break and reform billions of times per second. The fluid is dynamic, turbulent, reactive. Whether chemistry in such an environment could produce life or sustain it remains one of the deepest questions about K218b. Water, the molecule so central to life on Earth, becomes something unrecognizable under extreme conditions. Whether that transformation permits or prevents life defines the nature of this distant world. Albedo determines planetary temperature more than almost any other single factor. This number measures how much light a planet reflects back to space versus how much it absorbs. 0 means perfect absorption, all energy stays in the system. 1 means perfect reflection, all energy bounces away. Earth's albedo averages about 0.3. 30% of incoming sunlight gets reflected. 70% gets absorbed, warming the surface and driving weather. The reflection comes from clouds, ice, snow, deserts, and oceans at different rates. For K218b, to maintain liquid water with its thick hydrogen atmosphere, calculations demand an albedo above 0.9. The planet would have to reflect more than 90% of its star's light. This requirement emerges from energy balance. Greenhouse heating is so intense that only extreme reflection prevents runaway temperatures. Achieving 0.9 albedo requires exceptional conditions. Fresh snow on Earth reaches albedo around 0.8 to 0.9. Some ice fields hit 0.95 when newly formed. But entire planets cannot maintain snow-like surfaces. Something else must provide the reflection. Clouds become the obvious candidate. Cloud tops reflect sunlight efficiently. The whiter and thicker the cloud, the higher the albedo. Earth's brightest clouds achieve reflectivities around 0.9. But those are small features, not global coverage. K218b would need planet-wide clouds at high altitudes reflecting almost perfectly. The clouds would have to form a continuous layer. Breaks in coverage would let starlight through, reducing overall albedo. Maintaining such coverage seems implausible. The composition of these hypothetical clouds matters enormously. Water ice clouds reflect well, but require cold temperatures. Ammonia ice could work if ammonia exists at cloud-forming altitudes. Hydrocarbon hazes like those on Titan scatter light but absorb some wavelengths, reducing efficiency. A team at Oxford modeled K218b's cloud properties in detail. They calculated what types of clouds could form given the atmospheric composition and temperature profile. They found that even with optimal cloud composition and thickness, maximum planetary albedo reaches only about 0.6 to 0.7, far short of the 0.9 needed. Another team publishing results in April 2025 approached the problem differently. They modeled the radiation budget, assuming perfect cloud coverage below the observable atmosphere. Clouds so bright, they reflect like mirrors. Even with this unrealistic assumption, they calculated maximum albedo around 0.17 to 0.18. This devastating result means liquid water oceans are highly unlikely. The planet cannot reflect enough starlight to stay cool. Greenhouse heating dominates. Surface temperatures climb above the critical point for water. The cloud reflection problem dooms the simple Hessian interpretation. Unless some factor is missing from the models, K218b is too hot for traditional liquid water oceans. But models can be wrong. They make assumptions about atmospheric structure, chemical composition, and heat transport. Changing these assumptions changes the results. Maybe convection in the thick atmosphere transports heat differently than modeled. Maybe clouds have properties not captured by current theories. Exotic cloud types might exist that we have not considered. Clouds made from materials that do not condense in Earth's atmosphere but do under K218b's pressure and temperature. Metallic clouds, perhaps, formed from vaporized minerals that condense at high altitudes. Such clouds could have reflective properties, exceeding anything familiar. The hydrogen atmosphere itself might scatter light differently than nitrogen-oxygen atmospheres. Rayleigh scattering depends on molecular properties. Hydrogen molecules are smaller than nitrogen. They scatter blue light efficiently, but the star emits mostly red and infrared. The scattering might not help much with albedo. Some researchers propose that the planet's albedo varies with location and time. Maybe high latitudes have brighter clouds than equatorial regions. Maybe seasonal changes or atmospheric dynamics create periods of high reflectivity, alternating with lower values. A time-averaged albedo might permit habitability even if instantaneous values do not. This speculation stacks assumptions without strong physical justification. But the alternative is accepting that K218b cannot have liquid oceans, which then requires explaining the DMS detection without biology. The cloud reflection problem stands as one of the strongest arguments against K218b as a Hessian world. Physics and chemistry place hard limits on how reflective a planet can be. Current understanding says K218b cannot meet those limits. Either our understanding is incomplete or the planet is not what early interpretations suggested. The clouds refuse to cooperate with the habitable ocean hypothesis. They cannot be bright enough, widespread enough, or persistent enough to keep the planet cool. This problem awaits resolution. More observations might reveal cloud properties directly. Measuring the planet's albedo across different wavelengths would constrain cloud composition and coverage. Observing how brightness changes over time would show whether clouds are stable or variable. Until those measurements arrive, the cloud reflection problem casts doubt on one of the most exciting possibilities. A planet potentially covered in oceans and possibly hosting life might be too bright for its own good, or not bright enough, depending on your perspective. History teaches humility. Scientists have announced potential biosignatures before only to watch them collapse under scrutiny. Each failure refined techniques and raised standards, but each also damaged credibility and reminded us how easy it is to fool ourselves. The Viking landers arrived on Mars in 1976, carrying experiments to detect life. One experiment added nutrients to Martian soil and watched for metabolic gases. It saw oxygen release. At first, this looked biological. microbes consuming nutrients and producing gas as waste. Further analysis revealed the truth. Martian soil contains reactive chemicals, probably peroxides, that break down organic compounds and release oxygen without any biology. The positive result was a false positive. Mars was fooling the instruments through exotic chemistry. In September 2020, researchers announced detecting phosphine in Venus's atmosphere. Phosphine is pH 3, a gas produced by anaerobic bacteria on Earth. It should not persist in oxygen-rich or UV-rich environments. Its presence on Venus suggested either unknown atmospheric chemistry or potential life in the cloud layers. The announcement generated enormous excitement. Venus, our sister planet, possibly harboring aerial microbes, floating organisms living in the temperate cloud layers despite hellish surface conditions below. Within months, other teams reanalyzed the same data. They found errors in the original analysis. The spectral feature, identified as phosphine, might be sulfur dioxide instead, or an artifact of how the telescope processed signals. Independent observations with different telescopes could not confirm the detection. The phosphine claim evaporated. No clear evidence remained. What initially looked like a groundbreaking discovery became a cautionary tale about jumping to conclusions from marginal data. K2-18b itself has a history of misidentification. Early observations using the Hubble Space Telescope detected what appeared to be water vapor in the atmosphere. This excited researchers because water is essential for life as we know it. The findings suggested K2-18b might have a water-rich environment. Later observations with better instruments revealed the signal was actually methane, not water. The spectral features overlapped in ways that fooled the initial analysis. What looked like a promising biosignature turned out to be a different molecule entirely. These examples share common threads. Marginal detections interpreted optimistically, complex data with multiple possible explanations, confirmation bias pushing scientists toward the exciting interpretation, insufficient caution about alternative hypotheses. The DMS detection on K2-18b could follow the same pattern. The signal is real in the sense that something in the data deviates from a simple hydrogen atmosphere. But is that something actually DMS? Or could it be another molecule with overlapping spectral features? Methane absorbs in some of the same infrared wavelengths as DMS. Could residual methane signals be mimicking DMS? The team addressed this in their analysis, but perhaps not completely. Subtle calibration errors could shift apparent features to match DMS when the true source is different. DMDS and DMS themselves are hard to separate. The team acknowledges uncertainty about which molecule or what combination is present. This ambiguity means even if the detection is real, interpretation remains complicated. Independent verification is essential. Other teams must analyze the same data using different methods. They must reach the same conclusions through independent pathways. Only then does confidence rise to levels justifying strong claims. The James Webb Space Telescope is new. Astronomers are still learning its quirks and systematics. Early results from any new instrument sometimes include artifacts that look like real signals. Experience reveals which features are genuine and which are instrumental. The team behind the DMS detection has experience and used rigorous methods. They tested for systematics. They ran robustness checks. But history shows that even careful teams can miss problems. Peer review by the broader community provides additional protection against error. The paper invites scrutiny. Data will be shared. Other researchers will probe assumptions and test alternatives. This process takes time. Months or years might pass before consensus emerges about whether the detection holds up. Until then, healthy skepticism remains appropriate. The signal is interesting enough to warrant serious consideration, but not strong enough to claim definitive discovery. 3 sigma significance leaves room for doubt. Signals that fooled us before teach that extraordinary claims require extraordinary evidence. A potential biosignature on an exoplanet qualifies as extraordinary. The evidence must be ironclad before declaring success. K2-18b might be different. The DMS might be real and biological, or it might join the list of exciting announcements that faded when examined closely. Time and more data will tell.